Hi, welcome to this clip going through enthalpy and entropy linked together. I'm going to start by looking at the laws of thermodynamics in simple terms, and then link enthalpy to the first law of thermodynamics, entropy to the second law of thermodynamics, bring all of the enthalpy and entropy ideas together, and then finally look at a worked exam question which includes enthalpy and entropy calculations at the same time. Let's start by reviewing enthalpy. What I want to do here is try to bring together some first year work from Hess's law and some second year work from Born Haber cycles. To do this, we need to think about what the first law of thermodynamics actually says. It states that energy can't be created or destroyed, only transferred. So if we take Hess's law, that says something very similar, but it's talking about two different routes, perhaps, to get from the start of the reaction to the finish. So the start is where your reactants are, the finish is where your products are. So let's say we take this simple diagram to illustrate. Both routes will start and end with the same quantity of energy transfer overall. No energy is created or destroyed in either of the routes, so therefore the first law of thermodynamics has been obeyed. So if we compare it to a travelling analogy, let's say you were going from Liverpool to Leeds, for example, but your train was cancelled, so you had to take a connecting train to Birmingham, change at Birmingham, and get to Leeds. You take an indirect route, but you still end up in the same place. Your journey would be actually the same. So let's take our direct route, route number 1, going from A plus B to C plus D. Let's assume this is difficult to measure directly for some reason. A and B don't easily react directly to make C and D, so we have to go via E. So let's assume we've got two reactions. A plus B makes E, and then E can be made into C and D. And we can measure both of these directly. What that means is we can go via E to get from A and B to C and D. If we take an example of this, so we start with sulfur dioxide, reacting with oxygen to make sulfur trioxide. Let's say it's quite difficult to get it to happen straight away, directly, and we want it to go via the elements, so let's use enthalpy of formation data. What would normally happen is that the question would give you the data, and you can then put that in. So at the bottom you've got the elements in their standard states and the correct mole ratios. So remembering that we don't have an enthalpy of formation for an uncombined element, so the oxygen doesn't get an enthalpy of formation because it's always going to be 0. We insert the data values, so we take 2 minus 297s, and that gives us minus 594 on the left, and 2 times minus 441 on the right. Sorry, 2 times minus 441 I should say. Now you'll notice that you've got two arrows pointing upwards from your elements. Those are the arrows representing the direction of the enthalpy change, so the enthalpy of formation that is. If we wanted to go via the indirect route, the little dotted red arrow, we'd have to go against the enthalpy change arrow on the left hand side. So we reverse the sign of our minus 594 and make it plus 594. On the right hand side, the sign is kept the same because the direction of the route is the same as the direction of the enthalpy change. So the calculation gives us minus 288 kilojoules per mole. Now you need to remember that we've only combusted 2 moles of sulfur dioxide gas, but this doesn't represent the standard enthalpy of combustion for sulfur dioxide. We'd have to do 1 mole for that. So what we do is we call this the enthalpy of reaction instead, because it's in the molar quantities that this particular reaction is taking place. If we were to take this and extend it further to Born Haber cycles from the second year, the sum of all the energy transfers on the left hand side will equal the sum of all the energy transfers on the right hand side. So if we were to take delta LEH and minus 346 from the right hand side, and then compare it to going up the left hand side, you'd have plus 433, plus 79, plus 121, plus 376. So going down the right-hand side and going up the left-hand side will be the same. We can also apply Hess's law to lattice enthalpy. So the direct route is going to be, move this off the way there, the direct route on the right-hand side, going from the gaseous ions down to the solid lattice, is in black, and the indirect route is in red. But eventually, if you calculate them up, they'll be the same. So all the energy is accounted for. So again, the first law of thermodynamics is being obeyed. So let's take entropy. Entropy is used to explain spontaneous processes. So the second law of thermodynamics states that entropy tends to a maximum over time. I've got a couple of examples there. For example, a gas spreading to fill the space it occupies over time, or a pile of bricks being dropped out of a lorry. They're going to fall into a disordered, untidy pile, aren't they? They're not going to form a nice, neat pile automatically like that. There's lots of other examples of entropy you could use, and what we're interested in this video is the entropy in chemical reactions. So let's first of all take the entropy in physical change. We first of all take the x-axis to represent temperature and the y-axis to represent the change in entropy. At absolute zero at the origin, there is no movement of particles. None of the particles have any energy at all. They're absolutely static. But as you increase temperature by going from left to right along the x-axis, the particles will tend to vibrate more. And as the line suggests, the entropy will slowly increase because they're getting more disordered. But what's happening also is that there's a greater change in disorder at the boiling phase compared with the melting phase. So, in other words, when you melt something, some of the particles will still have attractions to one another within the liquid state. All of the particles have attractions to one another in the solid state. But if you were to go to the change from liquid to gas, boiling in other words, all the attractions have been overcome this time, so there's a much greater increase in disorder, so there's more entropy change. So if we take a simple example such as enthalpy change of solution, you can do a Born Haber cycle for this. We're going to work with potassium chloride. So potassium chloride happens to be found naturally dissolved in seawater at all temperatures, so whether the water is cold or hot. So the increase in entropy must account for why this endothermic process occurs by itself. So delta S must be a positive value. So hang on a minute, why must this be the case? Let's have a look. So if we take the free energy equation, delta G equals delta H minus T delta S, this helps to explain it. So just taking a moment to have a look at what it means. The Gibbs free energy change is measured in kilojoules per mole. Your delta H, which is the enthalpy change for the process of dissolving the potassium chloride, is also measured in kilojoules per mole. The temperature at which it takes place is measured in Kelvin, and the entropy change is the difference in entropy between the products and the reactants. So in this case, KCl, the solid will have an entropy, and K plus, aqueous, and Cl minus will have their own individual entropy. So the difference between them will be your entropy change. Now for this to happen by itself, in other words be spontaneous, delta G must be negative. So that means free energy is released to do work, in other words to dissolve the potassium and chloride ions into aqueous solution. For this to take place, obviously delta H minus T delta S must be below zero, because mathematically that's what you'd expect. If you think about T, it's expressed in Kelvin, which as an absolute scale is always 0 or above, that we talked about a moment ago. So if T is always positive, then the temperature is above 0 Kelvin. You can't get below 0 Kelvin, so therefore any temperature that you record is going to be positive. So if delta S is a positive value, so in other words an increase in entropy, then it's more likely that delta H minus T delta S is going to be equal to or less than 0. So obviously if you go from KCl, which is a more ordered solid, into dissolved K plus and Cl minus ions, which are more disordered, then there's going to be a positive increase in entropy. So that's going to be the case here. So all that has to happen is for T delta S to have a greater magnitude or size than delta H. So whether delta G ends up negative or not is dependent on the fine balance between delta H and T delta S. So take the plus 26 in kilojoules per mole and apply it to delta H. Let's say that, for argument's sake, our seawater sample, or our sample of KCl, I should say, as a solid, is at 298 K. If we have a positive value for delta S, which you do have in this case because you're going from a more ordered solid into a more disordered dissolved ions, then delta S will be positive. So like we said, delta G must be negative for free energy to be available. So if T delta S is greater than delta H at all temperatures, delta G will always be negative, and therefore this process will always be spontaneous. So let's link entropy to bond enthalpy now, another example of second year and first year thermodynamics coming together. So going back to our Gibbs equation, if we now home in on the part of it that's relevant, which is delta H can be connected to bond enthalpy by this simple expression. Now let's say we were to insert that expression into the Gibbs equation instead of delta H. You can then use the Gibbs equation to solve for an individual bond enthalpy. And that allows us to link Gibbs free energy with bond enthalpies from the first year. Another example of second and first year thermodynamics is Gibbs free energy being linked to calorimetry, which you might recall as Q equals mc delta T. So this time we're interested in delta H and temperature, again measured in Kelvin. So although the change in temperature when you carry out a calorimetry experiment might be in degrees Celsius, the increments of the Kelvin scale and the Celsius scale are the same. So you can simply take the temperature change and apply it in Kelvin as well. So let's say it increases by 4 degrees, it increases by 4 Kelvin. So looking at this, we're interested in the change in temperature. So this is obtained, move myself over here a little bit, there we go. This is obtained by taking experimental measurements of the temperature at the start and end of the reaction. So at any given temperature, its value in Kelvin can be inserted into the Gibbs equation. So it's useful to have a look at the units as well. I'm just going to move my head up a little bit so you can see just below where my picture is, C equals 4.18 joules per gram per Kelvin. Now you'll notice obviously that some of these values are expressed in kilojoules and other values are expressed in terms of joules. This is important because we need to make sure that when we're doing any calculations that we have comparable units. So we might have to sometimes change kilojoules back into joules if we're combining these two different sets of values. I'll show you an example of this when we do our exam question a bit later on. So just to recap there, delta H is in kilojoules per mole, but delta S is in joules per Kelvin per mole, and C, or the specific heat capacity, this time for water it happens to be 4.18, is joules per gram per Kelvin. Okay, so I've put myself up on the top right there. So we've got a reaction here. I've chosen a question that is a little bit unstructured and maybe slightly more challenging at first glance. So I can sort of deconstruct it for you and take you through it. So the reaction doesn't occur at room temperature. We're reacting carbon dioxide with carbon to make carbon monoxide. But we do have standard enthalpy data and standard entropy data. And it just tells you use the data given below to calculate the lowest temperature at which this reaction could take place or become feasible. So the first piece of processing is to realize that we're going to use delta G somewhere. And literally just putting that down gets you credit because you've realized that you're going to use it. They didn't tell you that delta G was relevant. They didn't mention it anywhere, so just putting that down actually gives you a mark. So the lowest temperature has to be when delta G equals 0. So when delta G happens to be 0, that's when the reaction is at equilibrium. So what we want is to find out the temperature at which delta G is 0. So that will be the lowest temperature at which this reaction can start to happen. Now to do that, we've obviously got to get delta H and we've got to get delta S. To do that, we need to actually do some calculating. So let's start with getting delta H. So we can bring in our Hess cycle idea from before. And we've had the reaction going across the top that we want. And we have our elements at the bottom. We know that we've got delta HF data, so that's formation. So we put the elements at the bottom pointing upwards toward the compounds they make. We pop the numbers in and we apply the reversing sign idea that we talked about before to turn minus 393.5 into plus 393.5. And that gives us positive 172.5 kilojoules per mole. So we can park that at the bottom, to come back to that in a minute. And now we can calculate delta S. So that's done by taking the entropy of the products and subtracting from that the entropy of the reactants. So that's 2 times the entropy of carbon monoxide, because we have 2 moles of it. Take away the entropy of carbon dioxide added to the entropy of carbon. So that's 2 times 197.6, take away 213.6 minus 5.7, giving us 175.9 joules per Kelvin per mole. So those are both positive values, and we can put those down at the bottom now. So like we said earlier, at delta G equals 0, delta H must be equal to T delta S. So once we've got those two equal to each other, we can isolate T. So at the minimum temperature, we now need to consider delta H in joules per mole, because obviously the delta S is in joules per Kelvin per mole. So I changed plus 172.5 into plus 172,500. So if 172,500 is delta H, we want T. So putting T on the left-hand side, making it subject, that means 172,500 divided by 175.9 gives us 980.7 Kelvin. So let's have a look at where the 8 marks might come from. As you can see the little 8 at the bottom. So checking the Markscheme, recognizing that we're using the Gibbs equation gets us a mark. Recognizing that spontaneous happens when delta G equals 0 or below. Calculation of delta H by putting either an enthalpy cycle like we did, or a calculation equation like they've done. So the delta H for the reaction is delta H for products minus delta H for reactants. Then putting the numbers in and arriving at a value gets you a mark. Then the same idea for delta S. So delta S is going to be the total entropy of the products, take away the total entropy of the reactants. That gets you a mark. Sticking the numbers in and arriving at 175.9 joules per mole per Kelvin. You get a tick there. And then for calculating T, there's 2 things to do here. First of all is to make delta G equals to 0, so therefore delta H equals T delta S. They've written it in a slightly different way, but essentially that's what we did as well. And then finally, to do the calculation, making temperature the subject gives us 980.7 Kelvin. Okay, hopefully this has been a useful review of some of the entropy and enthalpy values and ideas from A-level. So thanks for listening, and until next time, see you soon.